Hello everyone, this is Aditya from second semester IT department. This video lecture is about Lagrange multiplier theorem. The theorem is used for finding maximum or minimum value, or we say local maxima or local minima of a function in case where we have some constraints regarding the function. So the method which is used here is different from the conventional method, which involves if there is some function in terms of x, y, and z. And in the conventional method, we find the partial derivative fy, fx, fy, and fz. And then along with this partial derivative, we again find its a double partial derivative fxx, fyy, and fxy, like this, and which we call r, s, and t. So this is our conventional method which is used to find maximum or minimum value. Mind it, when we don't have any external constraint other than our main equation. So the advantage of using Lagrange multiplier theorem is that it used to find local or local maxima or local minima on the point for the equation where we have certain constraints. We can let's look at this with an example. If we have some function involving two variables, say fxy is equal to xy, and we have constraint which is x square by 8 plus y square by 2 is equal to 1. So here our original function is original function f is equal to xy, and the constraint function is this, which is a kind of secondary function. So what we do here that for any like this original function involve two variables, we shall find out its partial derivative for both the variables. Let's say partial derivative of f with respect to x, and we will equate it with some constant, arbitrary constant, which is known as Lagrange constant, and we shall also find the partial derivative of the constraint equation with respect to the same variable which we use for the original function. So in this case gx, here fx is partial derivative of original function, partial derivative, I'm writing short, partial derivative with respect to x of original function, and gx is partial derivative with respect to of a constraint function, right? So looking at this example, we will go with the procedure fx. Our fx is equal to y, and gx will be our, here this term will be, whole term will be considered will be constant, and so it will look like this, 2x by 8 lambda. Okay, so it will be equal to, y will be equal to x by 4 lambda. So this is our first case, and second we will differentiate in respect with y. So we will get x. So here we have two equations and two variable for equation. This is our equation 1 and this is our equation 2, and we have two variables x and y. So we can use any suitable method for finding the roots. So let's just consider multiply x to the first function and y to the second function, so that we can we can make the function LHS equal xy equal to x square by 4 into lambda, and on the other side we have xy is equal to y square lambda. So now we can see that our for both equations our LHS is equal. So if LHS is equal, RHS will be also equal. So we will get x square by 4 lambda is equal to y square lambda. So lambda will be cancelled, and we will get x square is equal to 4y square, which can be x can be plus minus 2y. Okay, plus minus 2y. X square by 8 plus y square by 2 is equal to 1. So we have come across this equation, and we will put the value of x, which is in terms of y, to the constraint equation. So we will get x square, we have 4y square. So in the place of x square we will put 4y square by 8 plus y square by 2, which will be equal to our 1. So here we will get y square by 2 plus y square by 2 equals 1, and which will be turns out to 2y square by 2 is equal to 1. So y square will be 1. So value of y will be plus 1 or minus 1. So here we get 4 points, which are plus 1, x 2 comma 1, 2 comma minus 1, minus 2 comma 1, okay, and minus 2 comma minus 1. So here regarding these 4 points, we have get all the points where we can find maximum or minimum value of the function. So putting this point or all these points in the original form, which is original equation, which is fxy equal to x into y. So if let us consider this point 2 comma 1, our first point. If we put this in the equation x into y, we will get 2. Second point will be 2 comma minus 1. This will be our x1 x into y will be minus 2. Again putting 2 minus 2 comma 1 equation will the value will be minus 2, and minus 2 comma minus 1 value will be plus 2. So regarding these points, on 2 points, which is 2 comma 1 and minus 2 comma minus 1, we get the maximum value of the function, our original function, which is xy. And 2 points 2 comma minus 1 and minus 2 comma 1, we get the minimum value of the function, which is equal to 2 and which is equal to minus 2. So now we have another question which involves 3 variables x, y and z, and the equation is and the question is we have to find the maximum and minimum value of the points of the function x, y, z, and also we have to find the points, and our constraint equation is x square plus y square plus z square equals 3. So we will proceed here with the same approach. We will find first of all f of x, which will be yz, f of y, which will be xz, and f of z, which will be xy. Similarly, we will go with g of x. G of x will be 2x, g of y will be 2y, and g of z will be 2z. So what we do, we equate the original function with lambda into the constraint function. So we have fx equal to lambda gx. Fx is our yz, and lambda and gx is our 2x, lambda into 2x. Similarly, fy will be equal to lambda gy, and fz will be equal to lambda gz. So our fy is xz and gy is lambda into 2y, fz will be xy, and gz will be 2z. So here we have 3 variables and 3 equations. So we can perform any kind of substitution to find these points. But the simplest one, which I prefer the most frequently, is multiplying with such variable, so that we can make the LHS or RHS equals every time. So here we can see that one variable is missing in every LHS. So we will do that. So we will multiply x, y, z, which will be equal to 2x lambda into 2x square, x, y, z equal to 2y square lambda, and x, y, z equal to 2z square lambda. So here we across that we have all 3 LHS equals. So equal LHS means RHS will be also equal. So we can easily compare all 3 RHSs. 2x square lambda equal to 2y square lambda equal to 2z square lambda. So lambda and 2 in every part will be cancelled. So x square equal to y square equal to z square. So here we can conclude that x equal to y equal to z. So now coming to the constraint equation, x square plus y square plus z square minus 3 equal to 0. Let us put x square plus x square plus x square minus 3 equals 0, which means 3x square minus 3 equal to 0. So x square will be equal to 1. So in this case we will get x is equal to plus or minus 1. So we know that x is equal to y is equal to z. So all 3 are equal. So all 3 will be equal to plus or minus 1. Here we will we have got 8 points. So the first point will be 1 comma 1 comma 1. Second point will be taking one negative sign, 1 minus 1 comma 1 comma 1, 1 comma minus 1 comma 1, 1 comma 1 comma minus 1. Third we can take 2 negative, minus 1 comma minus 1 1, minus 1 comma 1 minus 1, 1 comma minus 1 minus 1, and the further last point, all the 3 coordinates will be negative. So here we come across 8 such points. So on these 8 points the function will attain its maximum or minimum value. So we have to find on which point the function will attain its maximum or minimum value. Let us take first 1 comma 1 comma 1. At this point the function xyz will attain its maximum value, which will be plus 1, and it is its maximum value. And on the second sets of point, which is this, let me put this in box, and let's say the second set of point, I'm using Roman numerals to denote this. So for the entire set of second box points, we can say that the xyz will always be -1, which will be always the minimum value of the function. And the third sets of point, let us this call the third sets of point. For the third set of points, we have xyz always +1, again maximum, because there are two minus sign, which will cancel, two minus and minus will be plus, so we will again get +1 as our maximum value. And the fourth point, which is all negative -1, so xyz will be -1, which is again the minimum points. So here we got the maximum as well as the minimum points, as well as what the value attained, what the function value attained at that point. So here we go with the Lagrange multiplier theorem and its benefit. So it's a widely used concept in every part of our coding life. It is also involved in micro to micro economics. So the core idea is the optimization of gradient of the function f, which lies parallel to the gradient of the constraint function g. This is our core idea. So I'm just putting in it is in the form of equation. Gradient of f will be equal to, because it's parallel to the gradient of constraint function. So wherever the parallel comes, we know that a constraint is introduced. Let us call this constraint lambda. So lambda, which we were using everywhere in during the solving questions, is our parallel constant lambda, and then we have gradient of g. So this is the main concept of optimization. That's the basic idea about Lagrange multiplier theorem. Thank you.